jus de swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée jus dans la rougette des une pièce dans son chapeau. Dab dab, bidi 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 ba. Les rois du jazz manus, ma bini de ba. Une sentimentale venez tous. Cette soirée joue dans la rue, les rois du jazz manus. Mais jus de swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée jus dans la rougette des une pièce dans son chapeau. Dab dab, bidi 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 ba.
So, good morning everyone. Welcome to the third week of Type Systems for Correctness and Security. This is the official week this semester starts. So from right now on, everything will be kind of like on schedule, and like the lab is, the first lab is due next week. The second lab already started, but you got 2 weeks for that. But don't worry, you will certainly make it. It's enough time, I think, to do that. First, some announcements. So the video platform of the university is currently overloaded, as you might have seen. So I'm keeping the YouTube links a little bit longer, as the stream may drop out at some points, and you will lose a few microseconds or so. It's not ideal, but at least you get the lecture in its full length, at least to 99.99%. And the 100% solution will be then on the UPB video platform as soon as it's stable anymore. I was told this morning that they're working on it to make it more stable, to give it more resources, and to make everything technically a little bit more stable as it currently is. This was kind of to be expected because like the semester started and everybody is now looking at like videos from their home, and like the platform never had that much use before. So this was kind of to be expected. But as you've seen, like I got some backup plans, so there is no problem. I think for you, if that is the case, please let me know in the questions, and I will check if I can do something about it. If there is a particular problem that you have with like getting the resources for this lecture, but I hope this is not a problem for everyone. Yes, so for today, there will be a few changes. So today I will start with discussing the exercise solution for exercise 1 a little bit. So just to give you some hints how these solutions came to be. Sometimes just the solution is on the sheet and not like the thought process of like how someone can like come up with that on their own. So I'm trying to give that today in the first part of the lecture. And then we're going to have something completely new to me. We're going to have a little bit of an intermission of about 10 minutes, because this was requested in the last session. I did a little bit of a poll. Let's look at the final numbers. I just did before, but let's look at what we do have. And like them, oh, there was a new vote just in. So 15 to 4 people said they would like to have a 10 to 15 minute intermission in the live stream. This was a little bit weird to me because like you can pause this live stream anytime, but I was then thinking, yeah, the chat doesn't pause, so let's do that. I prepared a little bit something of you. So if you happen to do the intermission in front of your screen, you will see some nice cartoons. If not, then go to your coffee machine or whatever you like and then come back to the live stream at some point. Let's do 10 minutes today and see how this works. If there's not enough time, just let me know. Then we'll extend it a little bit to 15. But I think 15 is more than enough. That's the typical time I usually break during lectures anyway. So this is nice. Good. So with that, let's start with the exercise before we get into the new topic. And this is the solution sheet for exercise number 1. And the first thing we did is we were getting a little bit accustomed with mathematical foundations. So the first thing that we talked about is reflexive closures. So the task was supposed to be given a relation R on the set S. Define the relation R prime as follows. So R prime is R unified with S with like the tuples of SS, where S is always in big S, like in the set big S. So in other words, I usually try to do this in mathematical terms, but also like in prose. So you always have like this twofold thing. That is, R prime contains all the pairs in R plus all pairs in the form SS. And so every kind of like tuple of every element in S. And now we should show that R is the reflexive closure of R prime is the reflexive closure of R. So the idea of this proof is that you don't prove that is the case. So you assume that it's the opposite. So here we even go a little bit further. We say that we assume that R prime is not the smallest reflexive relation containing R. Reflexive closure, smallest reflexive relation. That's the idea here. And so from this assumption, it follows that there must be an R prime prime, which is a subset of R prime, which is also a reflexive relation containing R, because it's not the smallest. There must be some subset that is the smallest. No? And from this follows that for all S out of this set S, this big S, there is a tuple of this element, SS, which is included in R prime, and R is superset or equal to R prime prime. No? And from this follows that R unified with this S, this is the definition of R prime, is then a subset or equals to R prime prime, which contradicts our initial definition. Therefore, there cannot be such an R prime prime, which makes R prime the reflexive closure of R, the smallest reflexive relation. We cannot find a smaller one, so it must be the smallest. So that's the idea of this proof. So from the proof tactics here is you not always you can you do use the positive form of a statement, of an assumption. You can show that R is the reflexive closure of R prime is the reflexive closure of R, not by just showing that, but showing that there is no other case. And this is what happened in this proof. Good. I think I think most of you got that in the exercise, but just to be sure, I wanted to repeat that. That's all math, by the way, that you should have had at some time in your study. Good. We now at reflexive closures. Now let's look at transitive closures. And there we have this constructive definition of the transitive closure. So we have an R0, which is R, and an Ri plus 1, where this is Ri unified with a tuple of SU for some t, where ST is in the relation Ri and TU is in the relation Ri, then SU is also in the relation Ri plus 1. So if you have in the previous set and this Ri, in its previous relation Ri, you have the tuple ST and you have the tuple TU. Then in the next one, you also have SU, because it's transitive. So when something is when A is in the S is in the relation with T and T is in relation with U, then S is also in the relation with U, but just in the next set. So that's the constructive definition of that. In other words, that is, we construct Ri plus 1 by adding Ri. All the pairs can be obtained by one step of transitivity from pairs already in Ri. That's kind of another way of saying that. And then if you have such a constructive definition, you usually do like a full union of that. And this is this relation R plus as the union of all Ri. So if you have like the 0 definition and the I plus 1 definition, you can do a union and you have like this complete set of everything, even though it's not, it may not be bounded at all. You don't know that. That's not, that shouldn't keep us from doing that. And now we do, we have to show something, and we have to show that R plus is really the transitive closure of R. That is that it satisfies the conditions given in the definition of 225. That's the slide set that are already uploaded with the mathematical definitions. But that's just repeating basically what you did have. So if we need to show that it's a transitive closure, we first need to show that it's a transitive relation. And we do that by this little proof. So this line here. So let's start here. R is a subset of Ri is immediate by the definition, because R is R0 and this is included basically in every Ri. You see that up here? That's basically the case. Oh, interesting. My computer is updating in the background. So if you don't see me anymore, that was an update. And now we get two tuples out of this relation here. So ST and TU, we let that be out of this relation to show that S and U are also in Ri. So Ri minus 1 is a subset or equals to Ri. It must be smaller or equal because it contains the previous one, as we can see here, but it may contain more. So that should be true by the definition. Good. So we have two cases now. We show that both of these relations are, both of these tuples are in this relation, and either one or both are not in the relation. And for this case, if they are in the previous relation, it follows that this relation must be in Ri because it's part of the definition. So we can show that. So the more interesting case is the second one. So ST and TU are not in the relation. Then ST or TU are in the next relation. That means that because we have defined that up here, and they weren't in the previous one, that means that there exists a next relation. And in this next relation, then this thing is this SU is then extended by the definition. So there must be a newer one. Good. So basically, just to sum up, this shows that we do actually have a transitive relation. And now, as we need to show the transitive closure, which is the smallest transitive relation, which contains R, this is this R plus, we basically do the same as before. It's a pretty similar proof, but let's look at it. Good. So assume that we have an R prime, which is a subset of R plus. So R is a subset equals of R prime that is a transitive relation. We already shown this before. There's a space missing. Okay. That means that there exists an SU in R plus, and this SU is not in R prime, as R prime is a subset of R plus. We can say that. Then we claim if SU is in R plus, that SU is in R prime. So we claim the opposite. Then we see that SU is in R plus, and that follows that SU must be in R0, SU must be in R1, SU must be in Ri. And now we show that SU must be in this RK, some in between. And there it follows that SU, I have to mark this a little bit for you maybe, SU is in R prime. So we have a few cases again. So cases is K0, because we don't know K, this is this RK here. So K is 0, what happens then? If K is 0, then we say that SU is in K0, and SU is in R, the initial one, which is a subset of R prime, which means that SU is also in R prime. So we've shown it for K0. And next we do, this is basically, as you can see, this is basically like induction proof. You prove kind of the root, and then you prove the step. This is basically what we do here. So we say, okay, now from k minus 1 to k, what do we do then? So we say, assume that SU is in k. That means that there exists, by definition, an ST in the TU in the previous set in RK minus 1. Otherwise, it would be RK is the current set, K minus 1 is the current set. There may be the case, by the definition, if you look up here, there may be the case that you don't add something in there. If everything is already in relation with each other, you don't add anything more. So this is basically empty, the second part of the union, and Ri are basically Ri plus 1. This is the same. So this can happen. This is basically what happens here. And then we follow that ST and TU are in R prime, follows from the hypothesis. This is the hypothesis basically up here. And SU is in prime is because R prime is transitive. We already shown this up here. And this means that we have the smallest transitive relation found, which contains R. Well, that's basically what happened here. Good. As you can see, all pretty much like relations you should have had at some point in your math classes, and this is pretty much just repetition of that a little bit. So I'm a little bit faster here. Please do mind that. If there is a problem here with understanding, please let me know. But in general, I try to be a little bit faster with basic math here, because you should have had it at some point. It's just basically repeating. I also don't want to bore you. Good. So this was something that we actually had a question on in the Panda forum. Let's see if I hope I don't contradict myself in there. So we see that now we are thinking about preservation on the reflexive and transitive closure. This is what this is about. No? And now let's suppose that R is a binary relation on the set S and P. S and P is a predicate on S that is preserved by R. So this relation preserves this predicate on the set. No? And now we have another relation called R star. We need to show that P is also preserved on this R star. R star, just to repeat, is kind of the relation where everything is like reflexive and transitive. It's the closure. So we know that S is in relation with S prime, which implies that the predicate of S implies the predicate of S prime. That means predicate preservation, basically. And we know that R is kind of a subset of this R star. And now let's assume that when S is in this R star relation with S prime, P of S holds. So the predicate on S holds. Now we need to show that this also implies that predicate on S prime also holds. Good. So there are basically two cases that we need to check. That is that S is equal to S prime. So S and S prime are the same thing. This is pretty easy because the predicate of the same thing should be the same thing. If I do a predicate on one thing, it should be the same thing as a predicate on the other thing if they are equal. And that means that PS also implies PS prime. So this was easy. The more interesting case, of course, is when they are not equal. This is case 2, down here. That's where we are right now. And for this, we have that S and S prime are in the relation R plus. Remember the relation R plus? We just worked with that before. That's the transitive closure. Am I right? Yes. Good. how does this help us? Well, as you have seen, this transitive closure is kind of a union, yeah, of all RIs. So we need to we have two subcases basically. First thing is that S and S prime are in R, which is pretty easy because this is something by definition we already shown. This is basically the definition for here. If they are already in R, then we already know that this predicate here is preserved. So this was also the easier case. Second case is again the more interesting. So they aren't in R, but they are in Ri for the smallest I. Now we claim that S is in this relation Rk with S prime, and this implies that PS is preserved, so PS implies PS prime. This one here. For all k greater than I, greater or equal than I. No? Good. So there is kind of, the idea is that there is a set, the most smallest relation basically, where they are in a relation, and from that point on the predicate is preserved. That's the idea here. And again, as you can see, this already looks like an induction, and basically that's what it is. So we need to show that k implies k plus 1. So that's basic induction proving what we do here. Good. So we know that S is in this relation Rk with S prime. What does this imply? Here. So this tuple S and S prime are in Rk. This is basically another way of just writing this here. Or S and S prime are in Rk plus 1, without Rk. So basically in the addition that comes with this step. So they're either included in the relation Rk, or they're included in the next one. Good. So if this already is in the relation Rk, this is the hypothesis, so it's already implied. So we need to, again, the interesting part is again the step. So what we have here, so it's in kind of the right part of the definition of Rk plus 1. So the thing that comes afterwards. This means that there must be a T where St and Ts prime are both relations in Rk. Because it's transitive, we need to do that. Good. So St is an Rk implies that that Ps implies Pt. This is the same thing basically as the definition goes. Same goes also for the other relation. So Ps implies Pt and Pt implies Ps. And this means if we now chain them all together, because this implies this and this implies that again, we can say that if we have that, it also implies that the predicate is preserved. And this is how you do predicate preservation in this R star set, R star relation. So as you can see, we already exercised a few of the things that we talked about with its induction proof schema. As you can see, like all of these proofs were basically induction scheme based. And this is a good exercise basically for everything that we're going to do in the future in this course when it comes to proving. I think we have one exception, but everything else is induction proof. So if this comes natural to you, you're already well prepared for that. If not, have a look at that. Good. So I left out the exercise definition for that. So let me just pull up the exercise pretty quickly here. Where do I have that? There we are. Whoops, too big. Let me quickly fit that into the frame. Wasn't prepared for that by some reason. So, the exercise sheet, what did it call for? So, syntax. Syntax of a language defines the way it looks to us as a programmer and defines elements that can be brought to life using semantic rules. That's the idea. So, that was kind of the task you had to do. Consider a concrete definition of terms. So this is the definition that we had also on the slides. So this is a constructive definition of a syntax. And as you can see, basically the same thing as you've just seen with like raw mathematical objects, we now do with syntax objects. Good. So as you can see, like we have an empty set, and then we add like the we add like the terminals in there, and then we add all the constructive elements of the syntax, like successor, predecessor, is zero, and so on. And then the complete syntax is kind of the union set overall of this. And the question was now, how many elements does S3 have? We look at the solution. We already see this a bit. So this S0 of course has 0 elements, because by definition it just has, can I show this kind of side by side? Let's see. You don't see me anymore, but you don't need to anyway. Okay, if I scroll this a little bit. Haven't rehearsed this, as you might have guessed. So, and then put that over that. Now you see that. Okay, so S0, and now I need to do the same on my screen as well. Good. So S0 is an empty set. So quite naturally it follows that it also is kind of the size of the set is also 0. And now we do have I plus 1, which is basically all of this. And this is what we do here now. We count, so we have 3 things. We add 3 things, but as you can see, we have this ti here, and here, and here. So we need to multiply that by the with the previous items on the previous set. So 3 times S0. And then we have the if statement, which is basically 3 times a term in the previous set. 3 times a term in the previous set. So this is S0 to the power of 3. Because S0 is 0, of course the answer to this is 3. This is the only thing that comes out of this. Yeah, but now we have 3. So the term basically stays the same. It's always 3 plus 3 times the amount in the previous set plus the amount in the previous set by the power of 3 squared. Squared? No, cubed, sorry. Which is 39, of course. And then you can do the math again, take the same formula, and come up to 59,493. So there was a question. Aren't there duplicates when counting inductively? True is in pred 0. True is in pred 0 is in S1, but we counted again since 0 is in S1. I may not understand the question. Can you give an example for that I understand maybe? I'm sorry. So the thing is, if you count inductively, you take the amount of terms that is in this specific set, not in the addition. Yeah, pred 0 is an S1 and 0 is an S2. Yeah, but that's okay, because you just count the amount of things just right in this particular set. Yeah, you don't count just the additions, you count everything. Twice, white twice. Yeah, it's a set. It doesn't allow any duplicates. Aman had the solution for that. It's not a Java linked list or something like that. Good. I hope that answered the question. Let's go a bit further, maybe, just for a second or two. Good. Let me just quickly pull them over each other again. So, the next thing that we want to have is the concrete definitions. That concrete definitions are cumulative. And the idea is show that the set Si, that the sets Si are cumulative. That means that for each I we have an Si which is a subset or equals to Si plus 1. So you've already did that a little bit in math, so shouldn't be too hard. Let's have a look how the solution for this goes. Yeah. Okay, and as you can see, straightforward induction does the trick again. When I is 0, we have nothing to prove because there is no previous set. Okay, so it just vacuously is defined for that. And next, supposing that I equals j plus 1 for some j over 0 over equals 0, and that y is a subset of Si. That's basically the induction step. Yeah. Then we must show that Si is a subset or equals to Si plus 1. This is the ultimate thing that we want to show. That means for any term t in Si, we must show that this term is also in this Si plus 1. Yeah? So suppose we have t in Si. By definition of Si as the union of three sets, we know that t must be in one of the three forms. Yeah? So let's look at the definition again. Whoop. There we are. So the definition tells us we have basically three cases. It must be either in this set, or in this set, or in this set. Huh? Good. Good. We have the three cases. So t is in the set of true, false, or 0. In this case, we have that t is also in the next set by the definition of Si plus 1. Well, let's have a look at the definition again. It's always in there. You can't leave it out anymore. Okay, that was again a very easy case. So let's look at more interesting cases. So if t is either successor of t1, predecessor of t1, or is 0 of t1, where t1 is kind of in this Sj set that we defined previously. Sj is a subset of S1, so the previous set. And since Sj is a subset or equals to Si, by the induction hypothesis, we have this ti in Si. Yeah, so again, we can use the induction hypothesis here to show the previous case before we show the next one. And so t must be in t plus 1 by the definition of Si. Yeah. Good. Third case is the if again. And we already know that T1, T2, and T3 are again in Sj. And again, Sj is a subset or equals to Si by the induction hypothesis. So we have that T is in Si plus 1 by the definition of Si plus 1. So we basically did an induction proof on the definition of Si plus 1, and we just reused what's in there. As you can see, it's not very creative as a proof. It's very mechanical. Indeed, many of these proofs can be mechanized very, very easily, and people do that. So that's nothing people do by hand anymore. So all these little steps you automate basically away. Good. So the next exercise was on a different way of defining semantics. So now we talked a little bit about syntax, now we're going to talk about semantics. In the lecture, we have seen a small step semantics, and in the exercise now, we are concerned with big step semantics. Big step semantics basically tell us that we have this relation with this down arrow here, which is a relation between the set of possible values in the language, and the set of expressions. So it always gives you the final value of an expression. And that's why it's called big step, because it is doing everything in one step, one big step. No? Good. So we had you had for start this little incomplete big step semantics for n, so that values always evaluate down to values. We have already discussed this a little bit in the lab. I think this is basically where this idea came from, that driven a little bit of my design. I'm much more used to big step semantics, so maybe I misdesigned a little bit in lab 1, but we talked about this in Panda. Good. This is maybe where it comes from, as I see it right now. Yeah? And as you see the definitions, they not look so different from what you saw in small step semantics, but you leave out like all the middle steps. And so that tells you that if, like in the premise here, if t evaluates eventually to true and t1 eventually evaluates to value, t2 sorry, eventually evaluates to value 2, then the whole term evaluates to value 2. That's the be if true rule, basically. So you don't do the small step where you just rewrite the term. You just go down to the value. Same thing goes for the if false, and as you can see, this b suck is also. And the exercise now was to first define the complete definition for n in this big step semantics jargon, and then show its equality to the multi-step evaluation. Good, let's have a look how this goes. So this is the full complete semantics. So the b value, e if true, and b suck rule were already given, the first 4 here. So these, oops, no. Interesting how it marks things. Okay. So these 4 up here were already marked, and these are the others. So as you can see, it's just an application of the other rules. So you basically do the same. So for predecessor of T1, if T1 evaluates eventually to 0, of course predecessor eventually evaluates to 0. Same thing goes for this predecessor successor chaining that you had here. So if predecessor of T1 is what you consider, then T1 evaluates down to successor of an numeric value, NV1, then this NV1 is the result of predecessor of T1, because T1 is successor of NV1, and so this predecessor of this is then NV1 again. Yeah? Is 0, it's pretty much straightforward. That's what you expect basically. And then there is this T1, this is 0 successor rule, where you check that T1 evaluates down to successor of NV1, and this is must be false in all cases. So that's the complete semantics basically. Good. So equality goes like this. Now show that the big step semantics and the small step semantics coincide. So that this multi-step evaluation that we have here implicates this thing and vice versa. So we have this if and only if. That's how you read it. The if with the 2f. That means we have two directions. We need to show the first thing and then the other thing. So the first proposition is that if big step semantic holds, then it implies that this relation is also the case. And we do this, we prove this by first assuming that if we have such a T1 prime, where we can evaluate in multi-step form, then it is the case that we can also do this for the if and similar other terms by for other term constructions. This can be easily done by induction. We don't do it here. You could have done this, but in this case it is sufficient to just say we can prove this by induction because we already can. Good. Now we prove the proposition by induction on the derivation of this proposition up here, on the derivation of the big step semantics. And we do this by a case analysis on the final rule used. Big step semantics is in this case pretty easy because you always do this basically in one rule application. You can do this in one rule application, whatever you do. So B value is pretty easy because then the term is a value, which is immediate because it's a value already. You're already done. So then we do this for the B if true case. Then this is basically the term that were considered. And in big step semantics, it means we also follow from the rules that T1 evaluates to true and T2 evaluates to some value V. And from the induction hypothesis, we can then, as you can see, we're thinking about the subterms, and for the subterms, we can use the induction hypothesis. And from this, it follows that this here up here, this T1 big step evaluates to true, also means that it in small step semantics also evaluates to true. This is the induction hypothesis applied. And up there we constructed a lemma. This is this assumption here basically. This is what we call a lemma, a helping sentence basically. It follows that if we have this, if T1 and if T1 then T2 else T3, small step semantic wise evaluates down to if true then T2 else T3. If true tells us that if true, this is the if true rule from the small step semantics that we had before. That tells us that it is T2, and by the induction hypothesis we know that T2 evaluates in small step semantics to V. So this implies basically this. And then the result then follows by the transitivity of this of the small step semantics multi-step evaluation. It's transitive, so we can basically put it inside, and then we have shown that for the B if true case, This is the case. The other cases are pretty similar. You can do this pretty much the same for the be if false and for the successor and so on. I didn't write all of these cases here because they're so similar. Okay, but we still have something open. We need to show it's an if and only if, so we need to show the converse thing also. So this means if we have this multi-step, small step semantics evaluation here, then it also implies the big step semantic evaluation like this. So again, we do help us with a lemma. We established that this we do this for the if because it's much easier that way than proving at this point. And we say that okay, we have this form. So when if T1 then T2 else T3 multi-step evaluates to a V, then either T1 is true and T2 is V, or T1 is false in multi-step evaluation and T3 is V. So either case, when this goes, it must be either that T1 is true or false, and then either T2 or T3 must be V. It cannot be the case. This is pretty interesting. Moreover, the evaluation sequences for T1, T2, and T3 are shorter than the given evaluation sequence. This is something that right follows out of this depth predicate that we had. You can also do it with the size, but it's much easier with the depth predicate. So this is an interesting observation. This is basically similar for other term constructors like successor, predecessor, and so on, but the if is basically like the poster case because it's a much more complicated one. And this is proven by induction, by the length of the given evaluation sequence. Since a condition is not a value, there must be at least one step of evaluation. Also pretty decent. And now we can proceed by doing like a case analysis on the final rule in this step. This must be one of the if rules, because the others are so pretty much boring. Good. So we already established this. So from EIF we know that if T1 then T2 else T3, it implies that we have something that is if T1 prime then T2 else T3, and this evaluates down to some value V. So this is basically a combination of the if case together with the things we want to prove. And we also know from the if rule that there is a T1 prime where T1 evaluates to. So now by the induction hypothesis, either T1 prime evaluates down to true and V and so on and so on. This is something that we've seen before. So you can do both cases. And when we say that we now do this initial step, so this is the initial step that T1 evaluates down to true in multi-step, then we can just say, okay, T1 we can just exchange with T1 prime, and then this must also be the case. And this yield the desired result. This is the idea. And now it will be easy to check the resulting evaluation sequence are shorter than the original. So we already shown that it must be either false or true. By the induction hypothesis we can do that, and we have shown that T1 evaluates down to T1 prime. So we connected these two. Good. So that means we can now look at the subcases of E if true and E if false. And this is pretty much immediate, and this is also pretty much immediate, because we said that either T2 is V in multi-step or T3 is V in multi-step. And now we actually go to the actual proposition. By induction on the number of steps of small text evaluations given in the derivations of t evaluates down to multi-step evaluates to v. So if this happens in 0 steps, then t must be the value already, because we didn't take any steps. And then the result follows from b value. Pretty much easy, the easy case in the induction. Otherwise, we proceed by case analysis of form of t. Good. So then again, there is this if case. So if t is again an if, and by the lemma established above, we either have this t1 evaluates down to true, t1 prime, and t2 to v, and the other things and so on, or t is false. Both are valid. And the argument is so similar, than the thing that we just did before. It basically tells us and gives us gives us t1 evaluates in big step semantics to true, and t2 to v. And from these cases, we can then use the b if true rule to derive t is v. And then we can basically do the same for the other cases as well. That's especially much easier for the successor things or for the predecessor things. The if is always the most complicated one in this language. So we did it for this. Good. Before we already come to our break, let's look at evaluation. So first thing is like determinancy. And in determinancy, we wanted to show that if we have one-step evaluation, we have a definitive answer for that, and we have this deterministic answer. So if we t evaluates to t prime, and t prime evaluates to a t prime prime, then t prime and t prime prime are the same thing. So it's a deterministic evaluation. So this basically what we try to show. Good. It's a bit of a lengthy proof, as you might have seen. I'm just sketching it and following you through. You can read this on your own. I don't need to read this out loud for you, but I'm going to show you more the insights in this. Good. Also, as you can see, this is only the proof for B, for the B subset language of N. It works pretty much analogously for N, as you've seen in the previous proofs as well. We already just did that for the if. You can do this for N basically the same way. It's just more text. It's not more insight. So, and what you do is how do you prove such a thing? Again, induction on the derivations of t to t prime. And the idea is that at each step of the induction, the desired result is, we assume the desired result for all smaller derivations. So again, basic induction scheme. You assume the desired results for smaller derivations. So you just need to show the step. And the idea here is basically that you show that you can only derive one thing, and then you can prove by counterexample that t prime prime must always be the same as t prime. There cannot be another case. This is the basic idea of this proof in essence. So let's just look at one case of this E if true case. So if the last rule used in the derivation is t of t to t prime is the E if true, then we know that t has this form of this. So if t1, then t2 else t3, and t1 must be true. So otherwise we wouldn't have this rule. What we now need to see is that when we have this case and this form, does this match one of the other rules? as it does not, because E if false cannot be the case, and E if cannot be the case, because T1 does not evaluate down to another T1 prime. It evaluates the true, which is already a value, and it doesn't evaluate anymore. And we cannot have T1 is true and T1 is false. Conversely, if you turn your minds a little bit around, if we would have like a bad language definition, if we would not have determinacy, we would now see that. If we have like you can do small step you can do semantic definitions that are non-deterministic. But some people do this basically on purpose. But here we have a deterministic semantics, and that's what we wanted to show. And in this case, you would see that, because if you go through case by case, and you have a case that also where the kind of the preconditions also match another case, then you don't have determinacy anymore. And this is basically what you do here. You go through case by case and look, given the assumptions of this rule, do we also match another rule? And this is not the case, and this is and for this we've shown that it's determinate. That's the basic idea of the proof. Good. So conversely, if we would have like a faulty definition, we would now see that. And basically that's why in language design, if you actually design new languages and design new semantic rules and so on, you do these proofs to see that your definitions are in order. It's not just an exercise that everybody does. It's not a ritual. The idea is that you actually show this property on your definitions so they actually work. Good. Last thing on the sheet was show that for every term t there is some normal form t prime, so that t evaluates to some t a multi-step evaluates to some t prime. And this is a very easy thing. This proof is just in one sentence, and if you've seen like all the other things before, we use the size or the depth of the term. In this case, it's the size of the term, and we can observe that like every evaluation, it reduces the size of the term, or it's a value. And value means like it terminates. And if it reduces always if it always reduces by some size, that means that termination is kind of guaranteed. And bounded is this by like the usual order on the natural numbers is well founded. You can always bring it down to the order of natural numbers in this case. Good. This would have been like the solution to the exercise 1, taking like about an hour to do that. Are there any more questions for this exercise which I haven't answered yet? And I hope I answered the previous question with the things that are in the inductive definition sizing. Good. I did. Yeah, I had some help from Aman with that. That was a good point. I was missing that. Like, you were not thinking about sets, and that you can only have an element once in a set. I was assuming that kind of implicitly. Good. If there are no questions anymore. Sorry to interrupt you with the cartoons. YouTube giving me a copyright notice for those, so some music instead.
jeux de swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée joue dans la rougette des une pièce dans son chapeau. Dab dab, bidi 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 ba. Les rois du jazz manus, ma bini de ma. Une sentimental menu, venez tous. Cette soirée joue dans la rue, les rois du jazz manus. Mais jeu de swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée joue dans la rougette des une pièce dans son chapeau. Dab dab, bidi 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 ba. Les rois du jazz manus, ma bini de ma. Une sentimental menu, venez tous. Cette soirée joue dans la rue, les rois du jazz manus.
welcome back. This was nice. I got myself a coffee, so we might keep this intermission. Good. Sorry that I had to cut the cartoons, but like this YouTube notice was a little bit interesting because I was playing another YouTube video. So, well, okay. And definitely not by the owner. But either way, I hope you enjoyed the intermission. And now we are back with the second part of the lecture. Today we're going to talk about the simply typed lambda calculus. So last week we talked about the lambda calculus in general. So the syntax and semantics of the lambda calculus. And now we're going to talk a little bit about repetition, and we're going to think about how we can type that actually. So last week we also learned how to type the B and N languages, and we're now going to apply that to the lambda calculus as well. So in the B and N languages, it was quite obvious. Like we had booleans and numbers, but what do we have in the lambda calculus? So basically, what kind of type is this? Yeah, what does this mean? Basically type-wise. And let's have a quick look at the evaluation. So maybe there is a clue. So in the lambda calculus, you saw you had like two basic elements. You had function definition and function application, and function application is basically the thing where evaluation comes into place. So you have this two rules that basically progress you the two parts of the evaluation, the function and the argument, down to values, and the last rule is basically then the actual application of the function. No? That's what you should do. So what does this mean? So basically the interesting part is that we do need to check that we have functions. No? And let's make a little bit of a to-do list for the lambda calculus. So what do we need for a typed lambda calculus? So we need typing rules for variables. We need to know what like the types for variables are. We need to type abstractions. We need to know what abstractions are basically type-wise. And we need some typing rules how applications work. So which functions we can apply on which values basically. And overall, we want our type systems, of course, to be type safe, to satisfy preservation and progress, or preservation and progression as it's named here. And that needs to come pretty naturally. That's the idea. And we should not be too conservative if we go about that. No? That's the idea. Again, repeating what means to be conservative, we have seen like in the B and N languages that the typing rules that we had there were quite conservative. So if I had something like be true else zero, be true then zero else false, this would not be stuck. This would always evaluate to zero, of course. But we cannot say this statically without evaluation. So the type system was then pretty conservative to put this, and we're not trying to be too conservative here for the lambda calculus. Let's see if we can do that. So basic idea, what we can start for the lambda calculus is we're dealing with functions. So this is a function. Lambda x dot t is a function. So let's type that as a function, and like a function, let's use an arrow for that because we didn't have enough arrows already. Let's use this. So let's say this is a function. So again, repeating, the thing on the left is typed as the thing on the right in this colon. So abstractions are of type function. Let's start with that. But this has a problem because it means all of these would have the same type. So lambda x dot x, okay, this is a function, I can see that. Lambda x dot true, okay, yeah, this is also a function, but like this, the result of this might be a boolean, isn't it? If we have booleans. And of course, lambda x, lambda y dot y is maybe a little bit different than lambda x dot x, isn't it? Shouldn't it be? I don't know. So we have the feeling that we need somehow a more complex treatment. No? Otherwise, we would either be too conservative and would not allow such things, or we would be too like loose in our definitions, and we would not catch errors that might occur in runtime. We would not satisfy progress and preservation. So we need to find the correct corridor to do that. Let's start with a little bit of a different thing that we call family of function types. So just regarding everything as a function obviously isn't enough. So we need to think more about what function families look like. And this is what it does basically. It says, okay, lambda x dot t is typed as a function from type 1 to type 2. And this somehow feels natural because you have an input parameter, so this could be t1, this is the input type, and you have an output type, which is kind of the output of the function, which is t2. Yeah, this feels good. So let's see what we can do with that. But let's just first review like how to read this. So this abstraction, there's an S too much, this abstraction is of type t1 to t2. It's of this type. This is again a function type, but a family function type. Let me quickly note that down. Yeah, so let's have a look. So lambda x dot x is t to t. So we have more information now. We not only know that's a function, but also that the type of the input parameter is the type of the output parameter. Okay. What about this? This is again a function from t to bool. This somehow feels better. And this, so we have t1 that maps to a function from t2 to t2. And this is what we do have here. Yeah. So lambda y dot y is basically the same as lambda x dot x. So we have one type that maps to the same type. Yeah. But then again, we have a prefix called lambda x, which is then typed as t1. Yeah. And the interesting thing here, as you can see, is that type constructors are right associative. So they bind to the right. Even when I wouldn't have these parentheses here, it would still be valid because it's a function, it's the type of the whole thing, lambda x lambda y dot y, is t1 is a function from t1 to a function t2 to t2. And even when I would like leave the parentheses out, would still be the same. Just have a note: type constructors are right associative. So this seems somehow workable. Let's see how far we can get with that. Let's look at argument types. And let's change this a little bit up and say, okay, now we have this. Lambda x is of type t1 dot t2. So we change our syntax a little bit and denote in our input parameter what type it accepts. This is pretty much helpful, so we don't need to guess. And this is something that feels pretty natural when looking at other programming languages as well. Java does that too. When you define a function, they want to know the types of the arguments you do give there. At least they want to know object. And the way you do read that is you have a bound variable x, and this is of type t1. Okay? And if we provide then the types of the arguments, and then we help to guide the type checker. And this is what makes a language explicitly typed, because we write down the types of the variables explicitly in the language. If we wouldn't do this, this would be an implicitly typed language. Things like Python, JavaScript, for instance, you have implicitly typed languages. You don't denote the types of parameters of functions as you would in Java, for instance. In Java, you would denote the types of function arguments. And this is why they are called explicitly typed and the other languages are called implicitly typed. No, that's the basic difference between those two. So let's look at typing for once. So what does this mean? What is an argument type? No? We have a few new symbols on that slide. Let's have a look. You have this little turnstile, this little, can I paint on that? No, I can't. It's a browser. You have this little bar with this symbol, basically, in front of the conclusion. We come to that, what that means is a second. But let's decode this a little bit further. So that means that, like, afterwards you have you have lambda x, and x is of type t1. The body of the function is t2, a term called t2, and the type of the whole thing, of the whole abstraction, is t1 to t2, because t1 is kind of the input argument and t2 is assumed to be the output argument. Let's look at the premise of this statement a bit. Yeah? And in the premise of the statement, you see x typed as t1 left of the turnstile means that t2 is of type t1, this big t1. Yeah? What does this mean? The turnstile is basically giving us a means to talk about assumptions. So in the conclusion left of the turnstile there is nothing, so you don't do any assumptions there. This is always the case. In the premise you do make an assumption and say, under the assumption that x is typed as t1, t2 is typed as big T2, and this implies that under no assumptions, if you have a function definition lambda x of type t1, body is t2, this is a function t1 to t2. Yeah? What you do now is, in your head, the way you go up this derivation tree, you remember derivation trees, we did that last week. When you go up the derivation tree, you accumulate assumptions. Yeah? And that's the interesting thing. The idea is that we assume that occurrences of x in T2, and T2 is of type big T2, are of type T1. That's the assumption. And then we can conclude that the abstraction is of the type T1 to T2. Okay? But, as you see, terms might contain arbitrarily nested lambda abstractions. We already seen this in the last week a couple of times. Yeah? What does this mean now for our semantics? We need something more. We need a so-called typing context or type environment. Yeah, and we had this two-place relationship, this typing relation we had in the last lecture. We now exchange this by a three-place typing relation. So this is not a relation of a tuple, but this is a relation of a triple. You know? And this is the triple gamma. This is a Greek gamma, by the way. Then this turnstile symbol t types to t. No? Let's move to this. So this is gamma, and gamma is the set of assumptions about the types of the free variables in t. Yeah. You can omit this, as we've seen in the previous slide, yeah, when this is empty. But usually you write that. So this is the set of assumptions about types of free variables in t. No? And the idea is, under this set of assumptions, t is typed as big T. It will get a little bit more clearer once we go about and do this. how does this work? This is the general form of the abstraction rule. Please excuse these little lines above that. This is new. I updated my keynote last week and I think something broke. I haven't seen this until now. Just don't think about this little line above. It doesn't mean anything. It's some cause in the update, I think, did that. So the meaningful thing is basically the rule down there. So this is the abstraction rule for the lambda calculus. So this is the complete typing rule. I'm going to walk you through this a little bit, how to read that. So in the conclusion, you see this gamma again. So gamma turnstile, basically. Under the assumptions of gamma, we say that lambda x typed as t dot t1 and the function body is t2 is typed as t1 to t2 if gamma appended with x is big T1 under the both assumptions. So this comma is basically an append operator. You can see this as like a list or like a set. In this case, it's a set, and you do a set append in this specific thing. And under these assumptions, T2 is typed as big T2. And this comma extends gamma by adding new bindings on the right. You can do new type bindings on the right there. And this is how you collect these things basically up. You need this gamma because you want to be able to plug this into other parts of your proof. Of course, like on the start, on the very bottom of your proof, like your gamma is empty. But it fills up basically over time. You want to be able to plug that into specific parts. Good. Let's look at variables. So we did abstractions right now. Abstraction is one of the things on our checklist. Next thing is variables, and variables is pretty easy. This basically says under the assumptions of gamma, x is typed as t if x is t is part of this gamma relation already. So x needs already to be assumed to be t in gamma to be typed as a variable of that type. Or if you look at it inversely, if you find a variable, you add this definition, this explicit definition to gamma on the way up in the tree. It feels a little bit strange to define it this way, but if you then happen to have it implemented later on, and if you happen to make derivations, this will feel very natural, believe me. Right now it might feel a bit strange. At least I had this thing when I saw this first. Good, so we have abstractions, we have variables. So next thing would be applications, how to do that. But let's first look at that for a moment. I forgot that it's animated actually. So the type assumed for x in gamma is t. Oh yeah, this is the only thing? Okay, I could have spared that. So the type assumed for x and gamma is t, basically. That's how you read it. Okay, applications. Sorry for that. Application rule. The application rule basically is like this. So let's look, it feels like a monster, so let's start at the conclusion. So that reads, under the assumptions of gamma, T1 applied to T2 comes down to a type called T12. And how does this work? Well, two premises are necessary to make that work. So under the assumptions of gamma, that's the same gamma, by the way. That's the same set of assumptions. It's identical. Under this set of assumptions, T1 is typed as T11 to T12. So T1 must be a function from T11 to T12. And of course, the second premise then reads, under the assumptions of gamma, T2 must be of T11 in order to fit in there, because it's the input parameter to the function. So it needs to be the same type as the left part of the function type of T1. And this is T11. And the output type is T12. So that means that the output of the full term T1 applied to T2 is T12. Yeah? So if T1 evaluates to a function mapping, arguments in T11 to T12, and T12 evaluates to a result in T12, that means when applying T1 to T2, that will be a value of type T12. This is the idea. And this is pretty key. I think that's the rule you will use pretty often. Because this is function application. This is the basic bread and butter of Lambda calculations. No? Good. Let's look at what we did. So we on the way we changed a little bit about the syntax, but we didn't talk about it so much. So let's explicitly talk about syntax changes. So as you can see on the term side, on this T on the left, we made a little bit of a change. So we explicitly now name the type of the input parameter in the Lambda abstraction. Yeah, that's why it's called Lambda x colon T big T dot T in the T section now. Yeah? So then we also need to define kind of what is T. Yeah. And as we've seen that things are always function types in the Lambda calculus, yeah, that's what we do. So T is a function type from T to T. No? In values, we basically did the same syntax change, and we also syntactically added the gamma symbol. That's not actually necessary for a programmer in the Lambda calculus, but we need that later on for definitions. Also, if you want to use the typing environment during runtime later on, we also need to do that. Yeah, so the gamma typing context or typing environment we might need on the syntactic level, so we want to have that. Yeah. Also, we want to be sure how to add things, and then we define this little comma operator here, this little append operator also here in the syntax. Yeah, so we do have that in there. Good. So we have these new type annotations in summary, and we only have function types. Well, up until this point, we don't have anything else. What I did not introduce before is the so-called empty context. This is kind of this little empty set symbol here. It means that we have an empty context. We don't have any assumptions about free variables at the moment. And this is the term variable binding that we talked about. Good. In evaluation, of course, nothing changed. Typing does not change evaluation, and it shouldn't. It shouldn't interfere at all. It should coincide. It should help us not to make programs that get stuck, but we shouldn't change. We shouldn't introduce typing in evaluation right now. We need to do that when we do want to do runtime typing checks, but right now we don't need to do that. What we do is some syntactic change. We did this new type annotation here because Lambda abstractions now have this type annotation for input parameters. We also need to do this in the EAP apps rule. Yeah, but as you can see, as this T11 is not used on the right side, it does not have any meaning here. It's just syntactic and syntactic artifact. And these are our three typing rules that we just talked about. So the TVAR rule basically tells us when we have an assumption about X being in type of T in the gamma set in the typing environment already, we can say under the assumptions of gamma, X is in the typing rules. X is typed as T, sorry. Abstraction basically works as we talked about it. So when you go upwards in derivations, you basically push the you push the assumption about the free variable into the typing environment. So that means when you now go on to show that T2 is actually of type T2, a big T2, yeah, you already have in your set of assumptions that x is of type T1. You pushed the information about the free variables in T2 into the typing environment. That's what you did there. Yeah? And the EAB-ABS rule basically is just this matcher that tells us, okay, if T1 is a function from T11 to T12 and T2 is something of T11, then you can apply it and then you get something that is T12. No, this gives you the typing rule. No? Good. Of course, it's a typing relation. You can inverse it. This is usually helpful in proofs and whatnot. Yeah? And let's do that for a minute. And that's basically what we did already when talking about it. But let's do it explicitly. So if under the assumptions of gamma, x is typed as R, then x typed as R is in the assumptions. Feels natural. And same thing goes for 2 and 3. So if under the assumptions of gamma, lambda x is typed, where x is typed as T1, body of the function is T2, and the whole thing is typed as R, then R must be a function type from T1 to R1. Yeah? R2. R2? For some R2 with gamma x. Yeah, okay. This is where the binding comes. Okay. So the whole abstraction is of type R, and the target type is R2 for some R2, where under the assumptions of gamma and x is of type T1, one of the assumptions, T2 is of type R2. And then for the application rule, it reads, so if gamma under the assumptions of gamma, the application of T1 to T2 is R, then there is some T11 such that gamma, under the assumptions of gamma, T1 is a function type from T11 to R, and under the assumptions of gamma, T2 is T11. So when you go, this is basically the inversion, what you do when you go upwards in the derivation tree. Let's look at our to-do list. So what we did. So we did typing rules for variables, abstractions, and applications. We want to satisfy preservation and progress, and we not want to be too conservative. Okay, let's check. We have variables, we have abstractions, we have applications. We didn't talk about preservation and progress, and we didn't talk about conservativeness yet. Oops. Yeah, this is the downside of animations. So we want to talk about preservation, progress, and we're not want it to be too conservative. Now it works. Good. Uniqueness of types. So before we go into preservation and progress, we first want to show uniqueness. We already shown uniqueness for B and N, for our type system for B and N. This turned out to be helpful, so let's do that for the lambda calculus as well. Does it hold here? So the definition of that is in a given typing environment gamma. Because we added that. We need to add that to the uniqueness of types definition as well. So in a given typing environment gamma, a term T with 3 variables, all in the domain of gamma. The domain of gamma, it's a relation, as you can see. So gamma must have all the 3 variables in T in its domain. So that we must have assumptions about all the 3 variables that are included in T. And this term now has at most one type. This is the definition of uniqueness. So gamma must contain every 3 like definitions for all 3 variables in T. Then term T has at most one type. That means if a term is typable, so we can type a term, then its type is unique. Moreover, there is just one derivation of this typing built from the inference rules that generate the typing relations. So that means we have determinism in typing. we have only one derivation, one way of getting to that type, by these inference rules. So if uniqueness holds, we are already shown determinism of our typing. This is also very interesting. We also shown uniqueness, which is a much stronger property, by the way, but we also showed determinism, which is nice. It's true for now. It will change pretty soon. I already teased that in the last lecture. We will give that up at some point. We need to, but right now it's true. Good. Let's look at type safety. So type safety, as you learned, is the combination of progress and preservation. And let's start with progress. And progress for the lambda calculus works like this. So suppose T is a closed and well-typed term. So this is already a well-typed term. So that means under no assumptions, T is of type T for some big T. Then either T is a value, or else there will be some T prime where T evaluates to T prime in one step. So progression. We want to do progress in our evaluation. So that's the idea. And the proof for this is pretty straightforward. It's induction again, as you already have guessed, on the typing derivations. Works the same thing as for arithmetic expressions that we did in the last week. It's basically exactly the same proof for Boolean constants and conditions as we did before. But let's still look at this. So sorry, this is a wall of text, but so are proofs. So let's go through this and let's not shy away. The variable case cannot occur because T is a closed term. So the abstractions case is immediate, since abstractions are values. Doesn't work. So the only interesting case for this one is application. And when you have application, there is the form that this term that you're going to show progress for is in the form of T1 applied to T2. From the definition of progress, you already know that it's well typed. And if it's well typed, then under no assumptions, you have T1 is a function type from T11 to T12, and T2 is of type T11. You already know that. So then again, you have subterms, so you can use the induction hypothesis again. So either T1 is a value, or else it can make a step in the evaluation, and likewise can T2. It's either already a value, or it can take a step. So it's either the EAB1 or the EAB2 rule. And finally, if both T1 and T2 are values, then you can use this canonical form lemma that tells us that T1 has this form lambda x T11 dot T12. Oh, this needs to be subscript. Formatting can sometimes get lost, apparently. And so you can apply this EAB-ABS rule to T, and so it makes progress. So here you basically have shown all the cases where this thing can make progress. It cannot be stuck under the assumptions that you already have shown in progress. So this basically proves you progress for the lambda calculus. It fits on one slide. Isn't that amazing? I always find that amazing that you can show this slide and have basically shown the proof for progress. For preservation, we need to prepare us a little bit. We need to construct some structural numbers for the typing relation. Otherwise, we would get stuck in the proving process. So let's do that first. First lemma that we need to establish is permutation. And permutation means that if we have a well-typed term t as big T, yeah? And we have this delta, which is a permutation of gamma, yeah? Then under the assumptions of delta instead of gamma, we have the same typing. So the idea is that this gamma is not just a list of things. You can permutate the things around and still come to the same result. So what you basically boil down to that it's a set, but we didn't define it as a set because we want to append, so we need to have some permutation. Yeah, this is just technicality, as you can see. Moreover, the latter derivation has the same depth as the former. That means that it doesn't matter in which permutation you have this gamma environment, it always has the same depth as the other derivation. So there is no precedence here. And permutation gives us that we can permutate the elements of a context without changing the set of typing statements that we can be derived under it. This is very, very helpful. You can prove this by straightforward induction on typing derivations, that this always holds. Technically, you need to do this. I won't here because it's so boring. But you can just show that you can permutate this this assumption gamma, this assumption relation gamma in any way you like, and you basically come up with the same thing. Weakening is another thing that you need to define here, and weakening tells you that if you have a well-typed term t under the assumptions of gamma, so this is gamma turnstile t, big T. Yeah? So t is a well-typed term under the assumptions of gamma when as type big T. Yeah? And you need to see that x is not in the definition range of gamma. So x is not defined in this typing context. Then you can add x to this assumptions of gamma as type S, for instance, yeah, and you still come to the same typing derivation. Yeah? What this means is you can add more assumptions to the assumption set, but still come up on the same typing environments, on the same typing judgments. Yeah? T is big T, you know, is typed as big T, without any holding back. Yeah. Space. So you can basically add things to the typing environment without any harm to the typing judgments you can do, as long as the things you add have not already been in the definition range of gamma. No? And moreover, the latter derivation has the same depth as the former because you just add things to the typing environment. This doesn't change the depth at all. Now you can also do this by straightforward induction in typing derivations, that this won't change anything. Yeah? But we need these two things. We need permutation and we needed weakening to be actually be able to do the next step. So, preservation. Why is this so confusing? Because you need to take in substitution. Yeah? Remember from last week that when we apply an argument like a lambda abstraction to an argument, then we do substitution. We carefully constructed substitution last time, and a substitution is the key point in preservation, basically. You know, and this is why this reads for the lambda calculus in its following way. So, if under the assumptions of gamma and under the assumption that x is of type S, t is of type T, and under the assumptions of gamma, S is of type S, yeah, then under the assumptions of gamma, X substituted by S in T is of type T. Yeah. What does this mean? So you have typed S as S under the assumptions of gamma. So you have established that S is a well-typed term as the type big S, okay, under the assumptions of gamma. And when you now add that X is also of type S, and then T is a well-typed term, that means any free occurrence of X in T is of type S, then it naturally comes that you can just substitute any X that you have in T, in small t, with small s, because it's of the same type. And this is preservation basically, because like type preservation is only happening in application in the lambda calculus. It's only relevant there, because like for function definitions you don't need to preserve it because you don't do any evaluation. Basically, you only do meaningful evaluation for application anyway. So this is the interesting case for preservation. And you prove this again by instruction on the derivation of the statement under the assumption of gamma and xs, t is big T. For a given derivation, you proceed by cases on the final typing rules of the proof, and the most interesting cases are the one for variables and abstractions. Interestingly, because we thought about application, the whole thing, but now we need to show that all the prerequisites for that in the variables and abstractions actually hold when we put it into application. Let's go through this. So t var, this is the variable case. If this is the case, then t is in the form of some variable, so let's call it z, and z is type t, which is in the set of gamma and x is assumed as s. And in this case we have two subcases to consider, depending on whether z is x or whether z is another variable. Z might be x. We'll see. So if this is the case, if z is x, then when you exchange x with s in z, you come out with s. I just found out that the naming of the variable is very hard to say. It's better to read, actually. I should do more like G and H and something where you can actually like distinguish this a little bit better. But let's say okay, X, S, and Z. Well, I hope you follow. And the required result is then that under the assumptions of gamma, S is S, which is among the assumptions of the lemma. When you go back to the lemma that we defined, which is fine. This is good. So otherwise, Z is not X. Then if you exchange X and Z by S, you would come to Z. And the desired result is immediate because Z is already typed, and don't worry, it's already fine. You preserved. Good. Abstraction, much more interesting. Good. So if you have the case of abstraction, you can think about these things that are already given. So t is in this form. Let's say lambda y is t2, and then the body is t1. And the type of the whole term is t2 to t1. And what you can say about t1 is that under the assumptions of gamma and that x is s and y is t2, t1 is typed as t1, big T1. So we can now use the conventions that we introduced last time. And we may assume that x is not y and y is not in the free variables of s. And using now the permutation on the given subderivations, we can obtain that gamma extended with the assumption that y is of t2 and x is of s, t1 is of type t1. And using now a weakening lemma, this is why we needed that. On the other given derivation, that is gamma s and s, we can obtain that under the assumptions of gamma and y is t, yeah, this is why we need weakening. We can just add this y typing in there. S is S. Yeah? And now, by the induction hypothesis, yeah, which is gamma y, under the assumptions of gamma and y is t2, x exchanged by s in t2 is big T1. T1 is big T1. No? Now you can use the abstraction rule again, no? Which means that under the assumptions of gamma, lambda y typed as T2, and then x substituted by s in T1 is a function type from T2, the input type, to T1, the output type. This is precisely the needed result. This is very, very nice. Since by the definition of substitution, x substituted by s in t is gamma y typed as T1, so gamma y T1 in the function body, then x exchanged by s in T1. So this is pretty neat. So it is a circle, and then you have basically shown it for the T-abs case. Let's look at the T-ab case. Should be now straightforward, and it actually is. So doesn't seem very interesting. As you can see, the others were longer. So for the application case, now that we've established all of this, it's pretty straightforward. So T is T1 applied to T2. This is feels pretty natural, and T is of type T1. Yeah, and that means that under the assumptions that of gamma and x is S, T1 is typed as T2 to T1. Yeah, big T1, T2 to big T1. Yeah. And under the assumptions of gamma and that x is S, T2 is typed as T2. Yeah. And then by the induction hypothesis, you can derive this again. So gamma, under the assumption of gamma, if you exchange x by s in T1, you get a function that is typed as T2 to T1. And under the assumptions of gamma, if you exchange x by s in T2, you get T2. And by the application rule again, you get this nice definition. So you say that under the assumptions of gamma, if you change x by s in T1 and x by s in T2, and this is typed as T, that means that you can that is the same thing basically as when you do this in parentheses and exchange x by s in T1 and T2. Well, so it preserves. Pretty neat. Good. Let's do general preservation. So general, that was the preservation under substitution, and this is general preservation. Yeah. General preservation in lambda calculus basically tells you if you can have a well-typed term, so T is T under the assumptions of gamma, and you can do progress, so you have a T prime, yeah, that can evaluate in one step from T, then T prime is also of type T. So this is the general form of preservation. We now did this under substitution because this is a special case, and now we did the general one, and this feels a little bit shorter and more elegant to be true. Yeah? Good. We don't need to prove this because we already did it for substitution case. This is just the generalization of the whole thing. I just did the thing for substitution to be very explicit about substitution because it's the key point here, and this is just the smaller version of the same definition basically. The one is implied by the other basically. Good. I already hinted to you in the first lecture that we have interesting things when it comes to the lambda calculus and mathematical logic, also when it comes to typing and mathematical logic. And that's the so-called Curry-Howard correspondence. So this type constructor that we just did, this is this thing that sits in between the two things of a function type. We call this a type construction. Yeah? And interestingly, it comes with typing rules of two kinds. So you have an introduction rule. This is TApps. This is describing how elements of the type can be created. And you have an elimination rule. This is the TApp rule, basically showing you how these types, elements of these types can be used. Introduction and elimination are the two key points in mathematical proofs. Yeah, the so-called mathematical proof calculi. And interestingly, this is the link between those two fields, between mathematical formal proof calculi and type systems for models of computation. And this is basically the link between logic and programming. So you have now learned a very fundamental part, how computer science is rooted in math, and like how math uses computer science to automate steps that otherwise have to be done manually. Yeah? And the person that came towards this is first, like, you already know Haskell Curry, that was before, but also Alvin Howard, Hurrick Howard correspondence. He's always, I think, I didn't look it up, I think he's already still living. He was born in 1926. He's a mathematical proof theorist, and he is a professor emeritus, so he's already been retired at the University of Illinois in Chicago, the UIC. And he came up with that correspondence. He was the first to notice that there is such a correspondence between the parts that we do in computer science and the parts that people do in math. And there's a fundamental link between those two. And what did he come up with? So in constructive logic, in the constructive logic of proofs, of a proposition P. So you have, in logic, you have propositions, and you call them P usually. And this consists of concrete evidence for this proposition P. Yeah? And interestingly, Curry and Howard noticed that this evidence feels like strongly computational. Yeah, they found that while they were inspecting computer science, like the beginnings of computer science, that this part of mathematics feels strongly computational, and that, like, by some reason these things felt very interconnected. And they actually showed why this is the case. Not going to do into much detail, but just to show you what you can do with that. The interesting thing is, when you understand the one, you basically understand the other, and you can basically help each other out with that. Yeah. So the first thing that they noted is that propositions in logic are types in programming languages. It's the same thing. It's just a different name because of a different application, but it's basically the same thing. And you have these sub-propositions. So P is a sub-proposition of Q, basically, and this is a function type. And this is P, and this is a type P2Q. This is what we just learned. That's pretty interesting, because you can pretty much automate mathematical proofs using type systems. Automated proofs have developed in a little bit of a different direction, but as you can see is that they still share these roots, and they still have these same mathematical roots, and you can basically do the same with the others. So basically what you do in a type checker is nothing else than proving a program to some degree, to the propositions you say. And the propositions that we have are preservation and progress, given the types that we do have. The next thing I'm going to skip, because this is something of a later concept, is the so-called product type. We're going to talk about this in one of the next lectures. But interestingly, that in logic you have a proposition, and you also have a proof of a proposition. And the proof of the proposition in a programming language would be a term T of type P. So what you need to come up with when you have when you map proposition in logic to a type in the programming language, you just need to come up with a term that fills out this type, that just satisfies the type, in order to prove the proposition in logic again. You can then map it back, and then you have proved the proposition. That's pretty neat. Yeah. Furthermore, like if you show that proposition P is provable in logic, you can also say that the type P is inhabited. So there is some term for P that is actually valid. Vice versa, you can find types that are not provable, that don't have any terms that satisfy them. That also can happen. Very interesting observation. Good. Some advanced concepts for this. We're now going back to type. We're leaving mathematical logic. This was a little bit of an excursion. So you have like the whole picture of things happening. First thing is type erasure. And type annotations support the static checking of types. So type annotations, as you did in parameters now for functions, they support the type checking. And yet you don't need those at runtime. You've seen this in the EAP-APPS rule. There was a type annotation, and you don't need that at runtime. Anything you don't need at runtime basically can be erased. So in the Lambda calculus, you don't care because it's like inefficient anyway. But if you think about a programming language that compiles down to machine code that is actually executed, you don't want to bloat the program. You do want to remove everything that's not necessary for runtime anymore. And you can remove any kind of typing, any type of explicit typing to an untyped version, to an untyped state. And we call this program a process erasure. This actually happens during compile time. So it's not an abstract concept. And the way you do this is you basically define an erase function that removes any type information. And as you can see, that's pretty straightforward. For a variable, you don't do anything. For an abstraction, you erase the type from the parameter, and then you recurse down to the body. And for the application, you just recurse down to the two terms that you have. So pretty straightforward, nothing fancy. And just to show you, evaluation should commute with erasure. So evaluation shouldn't need your type information unless you have runtime type checking. Then you may need some type, but then you need to define your erase function in a way that you don't remove this information. So the idea is that t evaluates to t prime under the typed evaluation relation, then also under the also the erased terms, like the terms with the erased types should evaluate to the same thing. And if you erase of type t and then evaluate to some m prime under the typed relations, then there is a simply typed term t prime such that t evaluates to t prime, and so erase of t prime is m prime. And this is the definition for that the evaluation commutes under erasure, basically, so that evaluation is not concerned with typing information. We also need a definition for the so-called typable terms. So that means that a term m in the lambda calculus is said to be typable in this lambda with a little arrow. If there are, this is the simply typed lambda calculus, by the way, is a symbol for that, are typable in the simply typed lambda calculus if there are some simply typed term t, type t, big T, and a context gamma such that arrays of t in equals m, and gamma equals and then t is typed as t under the assumptions of gamma. So you can do you can type a term back even if it's in the untyped lambda calculus. This is pretty neat. So you can like pretty much transfer all the terms that we just defined in the last lecture, all the more complex things like the Y Combinator and such. Typing that is a little bit hard, but it can be done. Into the simply typed version without any hassle, because you have type erasure. That's also a pretty neat example for that. Good. So that concludes the simply typed Lambda calculus. So in this little roughly 1 hour and a bit, I showed you how we can type the Lambda calculus, and this will be kind of the substrate where we work on in the next few lectures on. In the simply typed Lambda calculus, we're going to extend that, and we show proofs on that, and we're going to do more complex computation and trying to type that and so on, and extend the type system as we go along. So this was based on chapter 9, if you want to read it up, and we now do have some time for some questions. You didn't stop me before, but maybe there are some open questions left. No more open questions. Well, okay. There's always Panda. Don't forget to do that. Just as an announcement, I will try to make the recording available on the university platform soon, but they told me they have a big queue of uploads that they need to process, so it might take a little bit longer than usual. So it might not be available by the end of the day. But as you already know, this YouTube link is working afterwards with the recorded version. And I seem to have forgotten to record on my machine the exercise session as well. So I'm going to pull that from the YouTube video as well. But I did record the lecture part today. So this will be available pretty soon. Yeah, let me know if you have any open questions. Don't forget that by next week, let me just check that for a while. By the 29th, so 29th, 8 a.m., this is the deadline for lab number 1. If you haven't already started, please do now. They do take a bit of time, especially if you've never programmed in Scala. This might take some time. I already received some submissions for that. Just heads up for people that already did submit. Your submissions already look quite good. You can't look into the results yet, but I can. And also, right after the lecture, we already went there. Lab number 2 is out there. This is concerned with type checking in the N language, that we had last time. So you basically need the contents from last week's lecture to do this lab, and this is due on May 6th, 8 a.m. Yeah, so you can do that. Be aware that you need the labs to get the course achievement, the so-called Studienleistung, and this is kind of the prerequisite for taking the exam, so please do them. Other than that, I hope you liked the exercise session today, where I discussed the solution a little bit more in detail. I hope this brought you some more insights into the exercise. If not, I'm already thinking about new things, how to do exercise sessions. So if you have a clue for me, please let me know. If you enjoyed the music at the start this time, let me know. Also, if you have some suggestions of music that we can show in the start. Also, if you have some royalty-free cartoons that we can show in the intermission, always open for that. The thing I tried today was apparently not free enough, whatever that means. Yeah, we will see about that. Otherwise, I will just show you something where I'm pretty sure that it's royalty-free, so that we don't block the stream. Good. If there are no more questions, and I don't see any more questions in the chat, I'll leave you to it. Also, the exercise sheet number, what's current? Exercise sheet number 2 has been available since Monday. Solution will be again on next Monday, and exercise sheet number 3 will come up also next Monday morning. So you can always start on the week with a new exercise sheet regarding on that. So exercise sheet number 2 is regarded with the untyped lambda calculus, so the thing that we had in the last week. And the next one will be concerned with the simply typed lambda calculus, so the thing we did in this week. So you have some time now to review the lecture and review the slides, and then work a little bit on the exercises for that. Now, also we're going to do a little bit of typed arithmetic expressions. So the exercise sheet that comes up on Monday is also a good precursor for the second lab, if you want to do that. But alas, you do have much time for that. Good. With this, again, I thank you very much for doing this spontaneous online course, and hope you have a good week.